Hello everyone and welcome back to another video. Today we're going to get started with the AN5 polynomial factors outcome. Some of the key ideas in this outcome include reviewing what a GCF is, or greatest common factor, as well as understanding what it means to factor polynomials, more specifically trinomials. To start us off, we're going to write 20 and 28 as a product of prime factors. Again, there's a few different ways to do this, but let's go ahead and use a factor tree. So with 20, we've got 2 and 10, and 2 and 5. I'm going to do the same here for 28. We've got 4 and 7, then 2 and 2, which means that 20 is the same thing as 2 times 5, and 28 is equal to 2 times 2 times 7. So those are my prime factors of 20 and 28, right? All of these numbers here are prime numbers, so they are considered prime factors of each number respectively. Taking a look at the GCF of 20 and 28, there's a couple different ways to do this again. Again, we could look at the prime factors and we notice here that 2 and 2, or 2 times 2, are the same. So we know that the GCF is the same thing as 2 times 2, which is 4. We could also use the cake method, where we have 20 and 28 here, and then we're going to divide them both by 2, and then we're left with 10 and 14, and once again we can divide them by 2 to get 5 and 7, meaning that the two numbers here on the left are 2 times 2, which is 4, and again giving us that GCF of 4. In case you forgot what the GCF was, remember that the GCF is the greatest common factor. And really what this is the largest number used to divide, and I should say largest whole number used to divide two or more numbers. So we can think of a GCF as that definition right there. Now, in the sense of factoring polynomials, we can define factoring as rewriting an expression as a product of two or more factors. Now, if you recall from earlier outcomes, a factor is really just any type of number. It can also be a variable that when you multiply with something else, it just simply gives you another number. So for example, if I think of the number 8, what are my factors of 8? I can think, well, I've got 1 times 8 and 2 times 4. So therefore, 1, 2, 4, and 8 are factors of 8. So 1, 2, 4, and 8 are all unique factors of 8. As for the GCF of a polynomial, we can simply define it as the largest polynomial that can be used to divide evenly into each term in the polynomial. So looking at this first example, what would be the GCF of 18xy squared and 27x cubed y squared? Well, the GCF in this case, we're going to start off by looking at the coefficient in each term here. So the coefficient 18 and 27, they have a GCF, or greatest common factor, of 9, because we know that 9 is the largest number that will divide evenly into both 18 and 27. Next, we're going to look at the x's. We have an x and an x cubed. Well, we want to think, how many x's can we actually divide into x and x cubed? Well, the most we can divide is just dividing it once. So x is the GCF of x and x cubed. It can't be x squared because we can't divide x squared into x. Finally, we're going to look at the y squared and the y squared. Well, we can divide y squared at most by y squared. So our final GCF of both of these terms is 9x y squared. So that was the quick method of doing this. Again, if we want to slow it down a little bit, what we can do is we can actually list the individual factors of each term. So looking at the 18xy squared, we can think, what are my factors of 18? Well, my factors of 18 will be 1, 2, 3, 6, 9, and 18. So those are all of the numbers that I can multiply together to get 18. What can I multiply to get x? Well, I can go 1 times x. What can I multiply together to get y? Well, I can go y times y, or 1 times y squared. Doing the same thing with the 27x cubed y squared. I'm gonna ask myself, what can I multiply together to get 27? So I've got 1 times 27, and then I've got 3 times 9. So those are my 4 numerical factors. Looking at my x cubed, what can I multiply together? Well, I've got x times x times x. I could do x times x squared, or I can do 1 times x cubed. Same thing with the y squared. I can have y times y, or 1 times y squared. So looking at my greatest common factor between all of these factors in each list, I can see that I've got a 9 and a 9. I've got an x and an x, and then finally a y squared and a y squared, leaving me with a GCF of 9x y squared. At this point, you can pause the video to try out these 3 practice problems. Once you're all completed, unpause and check your work. One thing that I'd like to point out here is that we have a coefficient of -10. I just want to make a little note to stick with factoring out just a positive factors for now. So there will be a time and a place where it's going to actually be better for us to factor out a negative number rather than just the positive numbers, but we're going to discuss that a little bit later on in this video. So in this next set of problems, we're going to factor or rewrite as a product each of these polynomials using the GCF of each polynomial. The first thing that we're going to do is identify the GCF of 5a minus 10. So in this case, the GCF is 5 because 5 is going to be the largest polynomial that I can use to divide both 5a and -10. So what that's going to do for me is I'm going to have 5 on the outside, and since we're rewriting this as a product of 2 or more factors, I'm going to put some brackets here. Now what the brackets do is it tells us, okay, we've got the 5 on the outside, we need to multiply the 5 by something on the inside to give us this original polynomial. Well, we can think to ourselves, well, we want 5a divided by 5 leaves us with a. Alternatively, we could think of it as 5 times something has to give me 5a. In this case, 5 times a will give me 5a. Same thing with the -10. 5 times something has to give me -10. Well, 5 times -2 will do just that. So the factored form of 5a minus 10 is just 5 times a minus 2. We can check our work by using the distributive property. We can take the 5 times a, and we can go 5 times the -2, which gives me 5a minus 10, which is what I had originally, so I know I've factored this properly. We can do the same thing here for the second example. Your GCF in this case, we can pull out a 2, or we can divide both the 2 and the 4 by a 2, so my coefficient will be a 2. And I can divide both the x squared and the x by x. So since my GCF is 2x, I'm going to put the 2x on the outside, and I can think to myself, well, I divided the 2x squared by 2x, what's left over? I simply have an x. So again, I can think of this as 2x times x gives me my original 2x squared here. The same thing can happen with the 2x times something, will give me a negative 4x. In this case, it has to be 2x times negative 2 gives me this negative 4x. Taking a look at this third example, the GCF in this case is going to be 2x yet again. So the 2x goes on the outside. And on the inside, I'm thinking to myself, 2x times something will have to give me 2x squared. So it has to be 2x times x gives me 2x squared, and 2x times something gives me a positive 10x. So we have x plus 5. For this last problem, again, we're going to split it up into each section here. So looking at the 6, the 24, and the negative 12, my GCF in this case between all three of those coefficients is going to be 6. Between the a squared, a, and a, it has to be a. And then the b cubed, b squared, and b is just b. So since that 6ab goes on the outside, we need to figure out what comes on the inside of the brackets here. So 6ab times something has to give me this original here. Well, we already pulled out or divided everything by 6, so we're just left with 1. A squared divided by a gives me a. B cubed divided by b gives me b squared. Taking a look at the 24ab squared, we went 24 divided by 6 gives me a positive 4. A divided by a just gives me a 1, so I don't need to write anything. And then b squared divided by b gives me b. Last but not least, negative 12 divided by 6 gives me a negative 2. A divided by a gives me a 1, and b divided by b gives me a 1. So I can actually go ahead and pull this bracket a little bit closer to give me a factored form of 6ab times ab squared plus 4b minus 2. So again, just a quick summary that a polynomial is in what we call factored form when we rewrite it as a product of two or more factors. So taking a look at these examples down at the bottom, we just want to be able to pick out the number of factors here. In this first example, we have 2 factors because we have 2 things that we're multiplying together. We have this 3 out in front, and this x minus 2 is what we call a binomial factor. If we take a look at the 3x minus 2 and the 2x plus 7, in this case we have again 2 factors, or 2 binomial factors. For this last example, we have 1, 2, 3 factors. On this page, feel free to pause, try out these 4 questions, then unpause to check your work. On this page, we're going to introduce the idea of binomial factoring. Now, binomial factoring really is the same thing as what we've done on the previous pages, except now instead of taking out a factor that is a single term or a monomial, we're now actually going to be factoring out a binomial. So before we get into it, I want to go to this example here on the side, and we want to think, all right, if we have 7xy plus 4y. In this example, if we were to look for the GCF, we would know that it would have to be y. We would factor out the y because it's a common factor to both 7xy and the positive 4y. Now what we would write as the second factor would be whatever's left over. So we have y times 7x would give us 7xy. And after we factored out the y here from the positive 4y, we'd have plus 4. So the way that we would write 7xy plus 4y in factored form would be y times 7x plus 4. We want to be able to apply that same logic to binomial factoring. We notice here that this x minus 3 and x minus 3 is a common factor to both the 7x and this positive 4. What that means we can do is we can factor that out, we can bring that out to the front, and we want to think about what's left over. And the thing that's left over is going to be 7x plus the 4. Now think about why we have these brackets here. Remember that the brackets means that we're multiplying these two factors together. We are not adding anything. If we factored out this binomial factor of x minus 3, the things that are left over will result in our second factor here. So we have 7x plus 4 as my leftovers, or really my second factor. We can do the same thing with a trinomial factor here. We know that the b plus c plus d is a common factor in each of these three. And what we're going to do is we're going to factor that out to the beginning. So b plus c plus d is my common factor. And what's left over is we have an a, we have a minus 2a, and then we have a minus 5a. Now, of course, we can actually simplify this one more time. This b plus c plus d will remain the same. If we take a look here, a minus 2a minus 5a, that gives me negative 6a once we have simplified everything. Once again, I encourage you guys to try out these three problems on your own by pausing the video and then unpausing once you've completed them. Our common factor here is our a plus 9, so I'm going to factor that out to the beginning. So the a plus 9 goes to the front, and whatever's left over ends up being my second binomial factor, which is 2a minus 3. I'm going to do the same thing in question B. So the x plus 5 and x plus 5 will be the same common factor, so that comes out to the front. So x plus 5 to the front. And we ask ourselves what's left over. So I have the 3x here. I have a 7, but don't forget about this minus sign there in the middle. So it's going to be 3x minus 7. Last but not least, we have the b plus c here and a b plus c. So that comes out to the front. And what we have left over, we have a 7a plus 21d. Now the thing that we need to keep in mind is we need to ask ourselves, have we fully factored out everything within each set of brackets? Well, if we look at the b plus c, there's no more common factors, so we're doing okay there. But the 7a plus 21d actually has another common factor. Well, we notice that we can actually rewrite this as 7 times a plus 3d. If you can factor out another common factor, then we haven't fully factored whatever our expression is yet. And what we're going to do here is we're actually going to take this b plus c and we can just pop it in behind here afterwards. Again, due to that commutative property of multiplication, I could rewrite it like so: 7 times b plus c times a plus 3d. Both of these expressions are mathematically the same. So on this page, we're going to talk about grouping, which is really just another type of common factoring used with 4 terms, where one GCF is going to be found for 2 terms and another GCF can be found for the other 2 terms. Now the idea behind this is to get the same thing left in both sets of brackets so that we can actually pull out a binomial factor towards the front of your expression. So let's go and see what's going on in this first problem. So we have 2ac plus 6ab plus 5bc plus 15b squared. You'll notice that we don't have a single GCF that is common to all 4 terms here. So with the 4 terms, what we've actually done, or what we're going to do, is we're going to split this up into pairs. So split it up into 2ac plus 6ab and 5bc plus 15b squared. Now in this case, we just so happen to have common factors between each of the first 2 terms and a common factor between each of the last 2 terms. Now that's not always going to be the case, which is why we put this little note here that you might have to rearrange the terms depending on what 4 terms you have. Now turning our attention to the first two terms, we notice that our GCF is going to be 2a, which means that what's left inside of the brackets, maybe I'll use blue here, what's left is going to be c plus 3b. All right, now we're going to look at our green pair here. And we notice that our GCF between 5bc and 15b squared is going to be a positive 5b. So I have to go plus 5b here. Now, if I don't put that plus, it's actually going to change our answer quite a bit. Because if I just put a 5b here, it means that we're going to start multiplying a lot of things together, which is not what we want. So we want to make sure that we definitely have a positive 5b, so plus 5b on the outside, and the factored form of these two terms ends up being c, or 5b, times c plus 3b. Now the cool thing that we're going to notice here is this takes us back to exactly what we just did on the previous page with our binomial factoring. We notice that we have a common binomial factor of c plus 3b in each pair. So we're actually going to factor that out to the front. So we have c plus 3b, and what's left over, we have 2a plus 5b. So we have factored out this expression here as c plus 3b times 2a plus 5b. So I have my two binomial factors here. Now, how can we be sure that this expression and this expression are exactly the same? Well, this takes us back to AN4 polynomial products, where we multiplied binomials together. So all we're going to do is, if I write down my factored form, c plus 3b times 2a plus 5b, and we're going to take this c here, we're going to multiply it with that second factor. Oops, that should be a 5b. 2a plus 5b. And then we're going to take that positive 3b and then multiply it with that second factor again. So once we go ahead and distribute, I have c times 2a gives me 2ac. C times 5b gives me plus 5bc. My 3b times 2a gives me positive 6ab. And 3b times 5b gives me plus 15b squared. Now, if we compare what we just got here to our original, we'll notice that we have exactly the same thing. The two middle terms are swapped, but that's okay. It doesn't matter what order you put these in because we end up with the same expression. So with the second example that we have here, again, we're going to pair them up, make sure that we have a GCF between each pair of terms. So my red pair and my green pair. Let's go ahead and find the GCF. So I've got a squared plus ax. My GCF is a. So what's left on the inside, a plus x. If I take a look at my green pair here, my GCF is going to be y, so plus y. And what's left on the inside is a plus x. So you're going to start to see a pattern when we are grouping and working with four terms here. Whenever we're grouping and we're trying to find the GCF of a pair of terms, we'll notice that whatever's left on the inside always has to be the same thing. Then we know we've done it properly. So I'm going to factor that out towards the front, a plus x as the common factor, and whatever's left over, a plus y, goes inside the brackets as my second binomial factor. For this last one here, it's actually going to be a little bit trickier than it looks. Again, same ideas, but we're going to have to do something a little different for the second pair here very shortly. So for this red pair, my GCF is going to be 6mn. So 6mn comes out to the front. What's left inside is going to be m plus 2n. So that will be my factored form of the expression in red. Now we're going to take a look at the plus 2n plus m portion of this expression. Is there a common factor between 2n plus m? Yes, there is. And it's actually just a plus 1. So our positive 1 is our greatest common factor between 2n and m. Now what's left on the inside? Well, we have 2n plus m. Now before we continue and say that the 2n plus m and the m plus 2n are the same, well, they are the same, right? M plus 2n is the same thing as 2n plus m, because all we've done is we've just kind of swapped the position of the two. It doesn't matter if we go 3 plus 4 or 4 plus 3, we still get the same sum at the end. So that's why we can consider these, even though they don't look exactly the same. Mathematically, they really are. What we can do is we can factor that out to the front. I will just go in alphabetical order, m plus 2n. And we'll take a look at what's left over, 6mn plus 1 is my second binomial factor. So I want to address a common misconception and a mistake that I see fairly often is, what's the importance of this plus 1 here? Why do I need that plus 1? Well, let's think about it this way. Let's go ahead and check our work by multiplying or using the distributive property to expand our two binomials here. So we're going to take the m times the 6mn plus 1, and then we're going to take the plus 2n times the entire 6mn plus 1. So we'll see what happens here. We have 6mn times n gives us 6m squared n, plus 1 times m gives us plus m, 2n times 6mn gives us plus 12mn squared, and then 2n times 1 gives us plus 2n. We notice that we have exactly the same thing as our original expression. We have the 6m squared n, we have the plus 12mn squared, and then the 2n plus the m right down here. So we've done it correctly if we can expand our factored form and come up with the original expression. So once again, just remember to include a positive 1 or a plus 1 if that is your only GCF between two terms. And again, our final simplified, our final factored form will be m plus 2n times 6mn plus 1. Once again, I encourage you to pause here, try out each question on your own, and then unpause to check your work. So for this next problem, I will let you know right now that we're going to have to rearrange it. So I'm going to put a little marker or reminder up here. So you will need to rearrange the terms here. Okay, so I'm just going to quickly run through why we'd have to do it. So if I were to do this normally, so we're going to factor my GCF in this case, which is 3. We're going to be left with an a squared plus 2b squared on the inside. And if I were to take a look at the second pair, I'd only be able to factor out, we can say we were going to factor out a negative a, for example. We'd be left with a positive 9 minus 2b squared. And you can see here that there's really nothing that we can do to make either of the factors inside of the brackets the same. So we are going to have to rearrange the way that the terms are displayed here. So you might have to play around with it again in any practice problem or example that you find maybe in a textbook or something. So what I'm going to do is I'm going to rearrange it so we have something a little bit more in common between our terms. So I'm going to start off with a 3a squared. I'm actually going to move this minus 9a right beside it because now I have a GCF between the coefficients and I have a GCF between the variables in each of these terms. I will keep the 6b squared over here, and I've got the minus 2ab squared right after. From here, I'm going to factor out the GCF in this case, which is 3a. I'm left with a minus 3. I take a look at the second pair here. We're going to factor out a positive 2b squared. Now I'm left with 3 minus a. Now here's the question. We have a minus 3, and then we have a 3 minus a. Well, that doesn't really help us out just yet. Our signs are actually flipped. We want a positive a in both, and we want a negative 3 in both. Well, the fix here is actually, instead of factoring out a positive 2b squared, we can actually flip our signs. We can take out or factor out a negative 2b squared. And what happens here is that we can actually rewrite this as negative 3 plus a. And we'll notice that if we were to just go right to left, we'd have a minus 3 or a plus a negative 3. So a plus a negative 3 would be the same thing in both sets of brackets here. So I'm going to go ahead and factor out that a minus 3 towards the front. And then what's left over is 3a minus 2b squared. If you're a little bit confused about why we're allowed to do this, we can think of an example such as negative 5. I can rewrite negative 5 in two different ways. I could rewrite negative 5 as negative 1 times positive 5, or I could rewrite it as 1 times negative 5. And that's really all we're doing here. We're rewriting these pairs, or this green pair, in factored form, with us having a negative factor here versus us having a positive factor. So it's like us using this version of the factored form of negative 5 versus this version. So mathematically, they're both the same, and this helps us, or these properties really just help us see that we can figure out or find the same factor inside both sets of brackets here. Last but not least, this one's a little bit tricky again because of that exponent of 2 on the outside here. So from AN4, we know that when we square something inside of the brackets, we're going to multiply it by itself. So we have m plus n times m plus n plus 5n plus 5n. Well, we already have our first pair, or our first part of this expression, in factored form. So this is the factor that we want. And what I'm going to do is I'm just going to go ahead and rewrite the second part here. Let's do this in green, actually. So this portion can actually be factored out as plus 5 times m plus n. Let's go ahead and just rewrite that first portion, m plus n times m plus n. And we can see here that the m plus n and the m plus n are exactly the same. So that factors out towards the front as our greatest common factor. And what's left over is the m plus n plus 5. So m plus n plus 5 comes out as our second factor. So again, if we were to multiply both expressions out, we would actually end up with the same polynomial. For this next section of the outcome, this is really the meat and potatoes of AN5. So we're going to talk about factoring trinomials, more specifically complex trinomials currently. So complex trinomials, if you guys were to take a look at maybe some textbooks or other internet resources, we define complex trinomials being of this form, ax squared plus bx plus c, where a is not equal to 1. Okay, we consider these complex trinomials. And really what this is just kind of like a general format for a trinomial at this point in Math 10C, where you have different coefficients. So we have your a here, you have a b, and you also have a c. These are going to be typically whole numbers, or rather integers. So we're going to have, for example, we could have an example such as 4x squared plus 3x minus 1, for example. And in this case, if we were to take a look at our coefficients, or our values rather, we would have in this case a is equal to 4, b is equal to 3, and c would be equal to -1. Now just remember that your coefficient also includes whatever sign is in front, whether it's a positive or negative. Same thing for your constant. term, if you have a constant of -1, then you need to make sure that you have noted that c is equal to -1. We can take a look at this example here, 6x squared plus 29x plus 35. We're going to look at our a, b, and c values. So again, we have a, b, and c. So in this case, we've got a is equal to 6, b is equal to 29, and c happens to equal to 35. So that's going to be really important for you to take note of right away. So at this point, some of you guys are wondering, well, why are we starting off with the complex trinomials? Well, we're going to compare these to simple trinomials later on, where a is actually just equal to 1. So you would have something such as x squared plus 4x plus 4 as an example. This is what we consider a simple trinomial. Now, the reason why we're starting off with the complex ones is because it gives us an opportunity to start off with decomposition, otherwise known as the AC method. There's a lot of other different ways to factor as well, but they more or less will all end up being the same thing. So starting off the complex just gives us one process that we can start off with that we can apply to simple trinomials. We can use that to factor a difference of squares as well. And really just any type of trinomial that we look at, we can use the decomposition or AC method to help us out. But first, we're going to look at how we do this with algebra tiles, and then we'll move on to the AC method. Now let's go ahead and start off with looking at the algebra tiles. Now on this page, I know they all look a little shaded, so we're just going to consider all of these being positive. So if we take a look at this first example, we've got an x squared here. We have an x, we've got 6 of those in total, and we have 1, 2, 3, 4, 5, 6, 7, 8 of these ones. So our actual expression being represented here is going to be x squared plus 6x plus 8. Now what we can do with those algebra tiles is we can actually rearrange them into a rectangular form as shown right here. Now what we need to do is be able to write an expression for the length of this rectangle. So if we're looking at the length coming down the side here, we can see that this length is going to be x. And we have 1, 2, 3, 4 lengths of positive 1. So we have x plus 4 as the length of this side. Taking a look up here, we want to look for the width of the rectangle. So let's go ahead and write x plus 4 over here. Taking a look at the width, again, this is going to be a length of 4, and we have 1 plus 1 there. So that gives us a total width of x plus 2. If we want to go ahead and write an area for this rectangle as a product of two binomials, remember that area is equal to length times width. So really we just have area is equal to x plus 4 times x plus 2. So if we were to write this in expanded form, let's move that down here, x plus 4 times x plus 2. Again, we're going to use the distributive property to help us out, x times x plus 2. So x times x plus 2. Then we're going to take the second term, multiply out the same thing. So we go plus 4 times that x plus 2. We're going to distribute this out. So x times x gives us x squared. X times 2 gives me plus 2x. Positive 4 times x gives me plus 4x. And positive 4 times positive 2 gives me plus 8. We can go ahead and add these like terms together, which gives us x squared plus 6x plus 8. And we know that's going to be the area. What we're going to do is we notice that this area, again, is really the same thing as what we started off with at x squared plus 6x plus 8. And we know that's the same thing that we put into a rectangular form here. So really all this does is it helps us see that anytime we multiply two binomials together, we actually end up with a rectangle. That's essentially what we're looking for when we multiply two binomials together. Again, because of that relationship to the area formula of A is equal to L times W. So now we're going to do the same thing, except we have two of the x squared tiles now. So we have 2x squared plus 3x plus 1 as our polynomial expression. Now keep in mind that an expression basically is differential, now keep in mind that an expression is different from an equation because there's no equal sign here at all. What we're going to do next is we're going to rearrange those algebra tiles into a rectangle and then state the dimensions, so the length and width of the rectangle as well. Now for this section, you can really orient the tiles in whatever direction you want. I will go ahead and do them like so. So I'll have 1, 2. Some of you guys might choose to have 2 of them stacked vertically. And then we want to place our 3 X tiles. Now this might take you a few tries once you're doing this on your own, but again, we're trying to make a rectangle here. So the way that we're going to do this is I'll have 1 there, I'll have 1 here, and 1 there, and finally that last positive 1 tile will come here in the corner. So you'll see we'll have a nice rectangular shape here. So to state the length of the rectangle, we can take a look along the top. We have a length here of x, x, and 1. So we have x plus, or rather 2x plus 1. And then along the side, we have x plus 1. So we have a length of 2x plus 1. And then we have a width. And then we have a width of x plus 1. So what we can do with our side lengths that we found here is that we can actually write it in factored form. So we can express this polynomial, 2x squared plus 3x plus 1, as 2x plus 1 times x plus 1. Or if you decide to put the x plus 1 in front, we can write it in this form. Both of them are mathematically equal to each other. So this next section here is what I largely consider to be one of the most fun parts of Math 10C. I know it's a little crazy for a math teacher to say, but I definitely believe that factoring is a really fun part of math. And again, moving forward into grade 11 and grade 12 math, factoring plays a huge part of each outcome that you're going to learn about in the future. So moving on with decomposition, or the AC method, again, the naming will differ from resource to resource. We're going to use that resource, or this method rather, to help us factor trinomials. So the first step is to always, if possible, factor out a GCF. So I'm going to put a couple of stars by this because factoring out your GCF at the very beginning makes your lives 1,000 times better. Now, again, before we start, that won't really mean a lot to you guys, but you'll see what we mean a little bit later on. Next, we're going to find 2 numbers that have a sum of b and a product of a times c. So again, we're going to review that as we work through these steps, but I'm just going ahead and highlighting some of the main portions here. And then we're going to write the second term using the 2 numbers from step 2, group the terms and factors, factor out the GCF from each pair, group the factors, and then we can verify our answer afterwards. So before we even get started, let's take a look at what we did back in AN4. So in AN4, we could use an example such as this. So AN4, when we multiplied things, so let's kind of contrast the 2 examples here. We've got 2x plus 1, for example, and let's go x plus 3 as our second factor. So in AN4, we learned that we would take that first term of the first factor, and we're going to multiply it with the entire second factor. Then we're going to take that second term of the first factor and multiply it with that second factor. And moving through our distributive property, 2x times x gives me 2x squared, 2x times 3 gives me plus 6x, 1 times x gives me plus x, 1 times 3 gives me plus 3. I can add up my 2 middle terms because they are like terms, so 6x plus x gives me 7x, and then I have the plus 3 there at the end. So you can see here in AN4 that the main focus was to use the distributive property to help us multiply out our 2 binomials here using the distributive property, and we work our way from 2 factors to give us 1 polynomial expression. Now in AN5, the biggest difference is that we're really just reversing what happened in AN4. So in AN5, we'd actually start off with our answer and we're going to try to make our way back towards here. So again, we'd have 2x squared plus 7x plus 3. And we're going to try to move backwards through our steps. So we're going to have to try to find a way to come back towards this step. And you'll notice here that this middle term, this 7x, is actually a result of us adding those two numbers there. So really what happens is we would break up this middle term, that's 7x, into plus 6x plus x plus 3. And then our next step after that is to, well, figure out what's going to happen with these two terms. So we're going to look back at these two and we're going to break it back into the 2x and the x plus 3. And how do we do that? Well, we'd have to take a look at these two terms and we'd have a GCF of 2x, x plus 3 gets left on the inside. And then let's use an orange color here. We're going to take a look at these two and we'll see that this gets factored out back into 1 times x plus 3. So 1 is my GCF, x plus 3 comes on the inside. And then we can simply factor this x plus 3 out to the front like we've done in the past. Then whatever's left over becomes my second factor. And we can see that we have essentially made our way back towards the beginning here, x plus 3, 2x plus 1. Again, the order that we end up with doesn't really matter. We can have x plus 3 times 2x plus 1, or we can flip it so we have 2x plus 1 times x plus 3. So AN5 is essentially undoing everything that we did back in AN4. Okay, so it's just the reversal of the steps that we took in the previous outcome. So hopefully what this does is it gives you a sense of what we're going to be doing in a more methodical sense in just a moment here. So again, we're taking what we did, what our result was in AN4, and we're just undoing all of that work to end up with two factors. So moving on to this page here, the first thing that we're going to do is we're going to identify your A, B, and C values. Okay, and we're going to see why we need to do that in just a second. So I've gone ahead, I've highlighted my constant term and my two coefficients here. So I've got my A value is equal to 3. B is equal to -10. Make sure you guys include that negative there when you are identifying each of your values. And then C is equal to +8. What happens here is, again, like we stated in the steps above, we're going to find two numbers that have a sum of B and a product of A times C. So we're going to start off with two numbers. So something times something is equal to AC, or A times C. So A times C is 3 times 8, which is 24. I want the same two numbers, so whatever numbers we have here and here, have to add up to give me B. So in this case, B is going to be -10. So to start us off, we're going to start listing your factor pairs of 24. So we've got 1 times 24, 2 times 12, 3 times 8, and 4 times 6. Now you'll notice that having strong mental math abilities will definitely make things a lot easier for you. So again, if you're not that great at times tables, that's okay. It will just take a little bit longer to get through those factor pairs on your calculator, but having strong abilities in mental math will make your lives a lot simpler in this outcome if you are able to do those off the top of your head. So the part that's a little bit tricky here is, you know that all these numbers will multiply to give you 24, but we can't have a sum of -10 at the same time. We could think of it this way. We could have a negative in front of the larger number, and that would give us the -10. And we would think that 2 times -12, or 2 plus -12 rather, would give us -10, which is what we want. But we still want our product to be positive. So the only way that this can happen is if we have both of the factors in each pair be negative. And the only one that would add up to give us -10 would be -4 and -6. So we can go ahead and write our factor pair down here. -4 times -6, does it give me +24? Yes, it does. And -4 plus -6, does it give me -10? It sure does. So what we're going to do with these two numbers is we're actually going to use that to decompose or break apart this negative 10, or this negative 10x rather, into negative 6x and a negative 4x. And we're going to leave the 3x squared and the positive 8 as is. So you can see, again, we've broken down this negative 10x using the two numbers that we found in this step. From here, this is going to be really just factoring by grouping. We're going to pair up the first two terms, and then we're going to pair up the last two terms. We're going to look for that GCF. So in this case, the GCF is 3x. We're left with an x minus 2 inside of the brackets. I'm going to factor out a negative 4 here. So what's left over? X minus 2. So once again, the key is to find the same thing inside of both sets of brackets, factor that out towards the front, and then take whatever is left, so the 3x minus 4, and then we have our factored form of our original trinomial. What we can do is we can also check our work by expanding our factored form. So we've got x minus 2 times 3x minus 4. When we multiply this out, we should get the original polynomial. If we don't, it means that we've done something wrong. We should go back and check our work. So taking a look at using the distributive property here, we've got x times 3x minus 4. And then we've got negative 2 times 3x minus 4. So from here, we've got 3x squared, x times 3x. Then x times negative 4 gives me negative 4x. Negative 2 times 3x gives me negative 6x, and then negative 2 times negative 4 gives me plus 8. And you can already see here that this step and this step are more or less exactly the same thing. So once we go ahead and add our two like terms together, we'll get 3x squared minus 10x plus 8. Since we ended up with our original polynomial, then we know we've done this properly. Now, a neat thing that we notice about this is that I actually have the negative 4x and the negative 6x in reverse order here, as opposed to the negative 6x and the negative 4x here. Does that matter? No, it doesn't actually, right? Because if I put the negative 6x here, it just means that I have the x minus 2 inside of the brackets. Whereas if I have the negative 4x beside the 3x squared, in this case, well, if we were to move in the opposite direction, we just have the 3x minus 4 in the brackets. So you can see that both of these end up giving you the exact same answer. Let's go ahead and try out another problem. So again, we're going to identify our a, b, and c values here. So we've got a is equal to 6, b is equal to 19, and c is equal to 10. So starting us off here, we have something times something has to equal to a times c. So in this case, a times c, 6 times 10, is 60, and the same two numbers have to add up to give us b, and in this case it's 19. So we're going to look for factor pairs that multiply to give us 60. So we've got 1 times 60, 2 times 30, 3 times 20, 4 times 15, 5 times 12, and 6 times 10. We can see if any of these pairs match up to give us a product of 60 and add up to 19. So in this case, it's going to be 4 and 15. So what I'd like to do is I actually like to fill in the blanks here. 4 times 15 gives us 60, so that works. And 4 plus 15 gives us 19. I like to do this because it just is another really a safety net in case we made a mistake somewhere. And as we're writing this down, it'll give you a red flag as to whether or not you've done this correctly. So I'm going to use the 4 and the 15 to break apart this 19x. And typically what I do when I try to decide, well, do I want the 4 or the 15 to come first, is I look at the coefficient here. So if I have a 4, or I have a 6 rather, I know that if I were to put the 4 there, I'd have a GCF of 2 coming out at the front. And if I put the 15 here, I'd have a GCF of 3 coming out at the front. So it just really depends on what you'd rather work with. Sometimes it's better to have certain terms up here first. I typically like to have the negative term. If this happened to be a negative 15, I'd put the negative 15 first. Again, it just really depends on your own personal preference. It doesn't actually matter what order you put it in. either 4x or 15x first. I'm going to go ahead and use the 4x. And the 15x comes afterwards. The 6x squared and the positive 10 are unchanged. What I'm going to do here is we can split these up into pairs. So factoring out the GCF of the green pair is 2x, and I'm left with 3x plus 2 on the inside. And from the blue pair, I'm going to factor out a positive 5, leaving us with 3x plus 2. So once again, we have the same terms inside of each bracket, so we can factor out that 3x plus 2 to the front. And then we are left with 2x plus 5. So once again, we're going to check our work by using that distributive property. We're going to multiply that first term, the 3x, with our second factor. And then we're going to take that positive 2 and multiply that with our second factor. We end up with 6x squared plus 15x plus 4x plus 10. We can combine our two like terms there in the middle. And we end up with 6x squared plus 19x plus 10, which is exactly what we wanted. At this point, you can pause the video, try out this next problem on your own, and then unpause once you've completed it. Now, before we get started on this last question here, I want to point us back towards the first thing that I noted on this page, is that whenever we're factoring, we always want to, if possible, to factor out a GCF before we even get started. Now, that's really going to come into play with this question here, where we have 10y squared minus 22y plus 4. We're going to end up with a much larger number, or some larger numbers to start off with. So let's imagine we didn't factor out a GCF here. And what that would look like is we'd have an A value of 10, a B value of negative 22, and a C value of positive 4. Now, these numbers are still manageable, right? Because then we'd be looking for two numbers that multiply to 40 and two numbers that add up to negative 22. But let's compare it to if we decided to factor out a GCF first. So I'm going to rewrite this after we factor out a factor of 2. So now this becomes 5y squared minus 11y plus 2. How does this compare? Well, we're just going to ignore this 2 at the beginning. We're only going to look at whatever's on the inside here. We have a 5, negative 11, and a positive 2. So in this case, we've got A is equal to 5, B is equal to negative 11, and C is equal to positive 2. So again, we're just going to ignore this factor of 2 on the outside. We're going to include that a little bit later on. So here we notice that each of the values are actually cut in half now. So again, with small numbers, it's not really a huge difference. It really matters actually at the last stage if you didn't factor out a GCF, but let's go ahead and continue on with these numbers. So we have two numbers that we want to have multiplied to equal A times C. So A times C is equal to 10. And the same two numbers have to add up to give us B, which is negative 11 in this case. So starting off with our factor list, we have 1 times 10 and 2 times 5. So we'll see here that because we have a product that's positive and a sum that's negative, the only way we can have a positive product when we multiply two numbers together is if both numbers are positive. And since we know that can't happen, then that means that both numbers need to be negative. So from here, we're going to see that the only combination that works is negative 1 times negative 10 gives us positive 10. And negative 1 plus negative 10 gives us negative 11. So both negative 1 and negative 10 checks out for both of our conditions here. So we're going to use that negative 1 and negative 10 to decompose the negative 11. So let's go with minus 10y minus y. We could put minus 1y there. Again, we don't need to. And I'm going to have 5y squared and the plus 2. Once again, we're just going to save for later that 2 out in the front. So we're just going to pair those two up, and then we're going to pair those two terms up. So I'm going to factor out a 5y. That gives me y minus 2. And then over here, I'm going to factor out a negative 1 actually. So we want to think, when we factor out a negative 1 here, we are left with a y in the middle. Again, if I were to multiply this out, negative 1 times y gives me that negative y. And we factored out a negative 1 from that positive 2. So that means that negative 1 times negative 2 needs to give me my original. And you can see in doing so, we have found the same factor, y minus 2, that we can bring out to the front. And what's left over is going to be this 5y minus 1. Now this is where we need to consider that 2 that we ignored at the beginning. And we can just bring that down to multiply out in front afterwards. And again, if you just do some quick math or quick mental math in your head, if you forgot the 2 here at the front, if you go y times 5y, that just gives you 5y squared. Just multiplying this without the 2 gives you what's in the brackets here. So you need to remember that we need to include the 2 out in front. Now some of you guys may be wondering, well, what happens if we didn't factor out that 2 at the beginning? Well, it would really just give you an answer that might look something like this. You might end up with 2y minus 4 times 5y minus 1. You might think, well, that's good enough, right? Well, not quite, because it's not what we consider to be fully factored. If you look at this first factor here, you'll notice that we could factor out a 2 from both terms. And this would end up giving you 2 times y minus 2, and then we'd have the 5y minus 1. You'll notice that if we were to do this, we would have the exact same factors as what we have originally done. So again, it just makes your lives a lot easier if you end up factoring out that GCF at the beginning, because chances are you won't get full credit if you leave your answer in this format. This would not be fully factored, right? And your teacher would also tell you the same thing. This would not be fully factored until you made sure that each individual factor is fully factored. So on this page here, we're going to be looking at what we call simple trinomials. And simple trinomials are when a is equal to 1. All right, so with the previous page, we looked at complex trinomials where a is not equal to 1. And in simple trinomials, the only difference is that a is equal to 1. Let's go ahead and work through a few examples together. So again, the steps haven't changed at all, really. The only difference is that a we know is going to be 1 for sure. B is equal to 5, C is equal to 4. We want two numbers that multiply to a times c. So in this case, a times c gives us 4, and the same two numbers have to add up to give us b, which in this case is 5. My factor pairs for 4 are 1 times 4 and 2 times 2. And you can see pretty quickly the only one that satisfies these conditions are 1 times 4 gives us positive 4, and 1 plus 4 gives us positive 5. Once again, we're going to use those numbers to decompose that positive 5. So I'm going to go plus x plus 4x. Then I have the x squared in front, and then the plus 4 here. Like always, we're just going to pair those two up, and we factor out a GCF in this case, which is f, or x rather, and then x plus 1 is what's left on the inside. I'm going to factor out a positive 4, x plus 1 is left on the inside. I'm going to pull this x plus 1 out to the beginning, or out to the front, and then what's left over is x plus 4. All right, fairly straightforward, nothing too crazy. Again, you can verify this on your own just by using that distributive property to give us the original polynomial. So again, with the second problem, we're going to note our a, b, and c values. So a is equal to 1, b is equal to 7, and c is equal to negative 60. So something times something has to equal to a times c. So in this case, negative 60, and the same two numbers have to add up to give us b, which is equal to positive 7. Listing off our factor pairs for, and again, we'll work with just the positive 60 for now. We're just going to ignore that negative in front. 1 times 60, 2 times 30, 3 times 20, 4 times 15, 5 and 12, 6 and 10. And then now this is when we consider that negative. If we have a negative 60, that means that only one of these numbers is negative, or only one column. So is it going to be the larger number or the smaller number that has to be negative? Well, we're going to look at our sum here. If we add two numbers together, and we know that one of them has to be negative, but our result is positive, then that means that our smaller number has to be the negative one. So doing that, we now know that the only combination that works is going to be the negative 5 and positive 12. And we can see by writing them down in our blanks here that we can confirm that. So as we've previously done before, we're going to use these two numbers to break down this middle term. And once again, it doesn't matter if we put the negative 5 or the positive 12 first, but what I tend to tell my students is that I put the positive term second. That way there's nothing too tricky happening with any negative signs. So the negative 5x plus 12x go in the middle. The x squared and the negative 60 stay the same. We're going to go ahead and split these two into pairs. So your GCF from the red pair is going to be x, and you're left with x minus 5 inside of the brackets. Your GCF from the green pair is going to be a positive 12, and you're left with x minus 5 inside of the brackets. From here, we can factor out an x minus 5, and that comes to the front. And then what's left over is going to be x plus 12. For this last question, I want you guys to keep an eye out to see if we can notice any shortcuts that we could possibly take while we're doing this problem. As always, I've identified my a, b, and c values, where a is 1, b is negative 8, and c is equal to 15. From here, I know that I need two numbers to multiply to give us a times c, which in this case is 1 times 15, gives us 15. And the same two numbers have to add up to give me b, which is negative 8. I list each of my factor pairs, 1 times 15 and 3 times 5. Since my product is positive and my sum is negative, the only way I can have a positive product is if both numbers are positive or if both numbers are negative. So this means that both of my numbers in this case have to be negative, and the only one that matches up with both a product of 15 and a sum of negative 8 are the numbers negative 3 and negative 5. Now something that I want to point out to you guys right now is when we take a look at some of the numbers that we've chosen for the previous two problems, if we look here, what do we notice about these two numbers and our final factored form? What do you notice about these two numbers and the final factored form here? Well, really all we're doing is we're taking these two numbers and they slot right into our factors. So what we can do is we can actually go straight away from this step and say that the factored form of x squared minus 8x plus 15 is simply going to be x minus 3 and x minus 5. Most textbook resources or any other internet resources typically call this factoring by inspection, where all you do is you take a look at your product of AC and sum of negative 8 to give you your two numbers that will later just become your factors of your original trinomial. The most important thing to note about this shortcut is that this is only possible when a is equal to 1. If we go back to some of our previous examples, we'll notice here that we can't simply put negative 4 and negative 6 into our factors here at the end. We cannot put the factors, or we cannot put the numbers 4 and 15 into our two factors here. So that trick, or shortcut really, only works when a is equal to 1. For the next three problems here, I encourage you guys to use either factoring by inspection or just decomposition in order to factor each of these three problems. Pause the video and then unpause once you've completed your work. For these next three problems, you'll notice that they're going to be a little bit trickier. For the first two, you might have to do something such as factor out a GCF, or you might notice that there might be more than one variable. So take a look as I factor out a GCF from D and E, and then I work my way through F. Remember that you always have to include the GCF that you factored out right at the beginning, otherwise your final factored form will be incorrect. There are a few different ways we can approach this last problem, but typically There are a few different ways to approach this last problem, but typically what I tell students is to simply ignore that extra variable. So we're going to ignore the y for this middle term, and we're going to ignore the y squared at the end of your third term. Then we are going to factor this using decomposition. We have a is equal to 1, b is equal to -4, and c is equal to +4. From here, we'll know that our two numbers have to multiply to a times c. So in this case, +4, and the same two numbers have to add up to give us b, which in this case is equal to -4. So you don't have a ton of choices here, but we know that we'll end up with -2 and -2. And what we're going to do is we're actually going to split these up into -2x and -2x. And this is when we can start to consider those y's that we took out at the beginning. So from here, I'm going to break down that -4xy into -2xy and -2xy. I can reinsert this as the +4y squared, and my x squared comes out to the front. I can then factor out the GCF from the first two terms, which ends up being x, and I'm left with x minus 2y. Then I'm going to factor out my GCF from the second pair, which in this case is going to be -2y. And then we're left with x minus 2y inside of the brackets. I can factor out an x minus 2y to the front. And then I'm left with x minus 2y. So again, even though a problem looks a little bit different, really all we need to do is essentially minimize this problem so that it becomes something a little bit more familiar to us. Here we can take a look at a special type of trinomial. So once again, we're going to start off with identifying our a, b, and c. So a is equal to 1, b is equal to 2, and c is equal to +7. We know that we need two numbers to multiply to give us a times c. So in this case, it's 7. And those same two numbers have to add up to give us b, which is 2. The only combination that we have to multiply to 7 is either 1 and 7 or -1 and -7. But neither of these combinations will add up to give us b. Therefore, in this case, this trinomial is actually what we call a prime trinomial. So this is a trinomial that's actually not factorable, at least in grade 10. Later on in Math 20, you'll actually learn that you can factor this, although the solutions won't make quite as much sense as they would later on once you've actually learned the new content. On this page, we're going to talk about a special type of trinomial called a perfect square trinomial. At first glance, they look quite similar to some of the trinomials that we've already worked on in the past, but there are a couple of special properties that we want to examine on this page here. So the first thing that we could do is we could factor this using inspection, and this would end up being x plus 5 times x plus 5. Again, the reason why we're allowed to do this is because our a value is equal to 1, so we can simply factor this using inspection. Again, we could use decomposition to factor this out, but just for the sake of time, we're going to skip ahead and give you the factored form here. So the first special characteristic of this type of trinomial is that we notice that both of the factors are exactly the same. So because they're exactly the same, we can actually rewrite this as x plus 5 all squared. Now recall the reason why we're allowed to do this is because each of these factors, because they're the same, we can actually combine them. Think back to a case where if we have something like 4 times 4, we can actually represent this as 4 squared. So we can represent this x plus 5 times x plus 5 as x plus 5 squared. So as a result, because we can express this trinomial as a perfect square, we can call it a perfect square trinomial. For our second example here, we can go ahead and do the same thing. We can factor by inspection and say that we've got x minus 3 times x minus 3, which we can further simplify to x minus 3 squared. So now the question that I want to pose to everyone is, can we find any relationship between the x squared and the x, the positive 25 and the 5 here, and then finally this positive 10x with both the x and the 5 here? We can ask the same questions about the x squared and the x, the positive 9 and the negative 3, along with this negative 6x and both the x and the negative 3. If you're very observant, you might notice that 5 squared here gives us 25, and x squared, well, is obviously x squared. With the 10x here, it's a little bit trickier. All we're going to do is actually take 2 and multiply it with our x, and then multiply it with 5. We'll notice that the same pattern applies with the x here. Again, x times x, x squared. Negative 3 squared is the same thing as positive 9, because negative 3 times negative 3 gives us 9. And this negative 6x actually is a result of 2 times x times negative 3. So that actually leads us into the general form of a perfect square trinomial, x squared plus 2xy plus y squared, where all we need to do is really just look for the first term, which is going to be a perfect square, the last term that's going to be a perfect square, and our middle term is made up of taking 2 times the square root of our first term, and then we multiply it by the square root of our last term. That might be a little bit tricky for some of you guys to understand right now, but as we take a look at a couple of examples, it might start to make a bit more sense. So with our first example, we've got x squared plus 24x plus 144. We can ask ourselves, is x squared a perfect square? Yes, it is. And is our last term a perfect square? Yes, it is. So what we can do here is create our two factors. And since we have a perfect square for our first term, perfect square for our last term, we can be about 90% sure that we have a perfect square trinomial. Now the last thing that we need to examine is our middle term, and we know that it has to be 2 times the square root of our first term times the square root of our last term. Let's see if that works out. We know that the square root of x squared is x, so I'm going to go ahead and pop an x into our first term of each factor. We'll take a look at the 144, and we know that the square root of 144 is 12, so I'll pop a 12 into, or as our second term in each factor. And then in order to figure out if this is going to be a plus or a minus in both of these, we simply look at the coefficient. Since this is a positive 24, we know that we are going to put a plus for both of these. The last piece of verification that we need is to make sure that we can go 2 times the square root of x squared, so 2 times x, times the square root of 144. If all of this multiplies to give us our middle term, which is a positive 24x, then we know we've done it properly, and we have a perfect square trinomial. Now, of course, we can simply factor this regularly. We can factor this using decomposition, or we can factor this using inspection. And I'd actually prefer for most of my students to work with decomposition instead. Decomposition will never lead you astray. So I'd actually recommend that you don't rely on memorizing this general form too much. So again, whenever you're in doubt, just use decomposition. It will never lead you astray. Taking a look at a different example here, we can see that we've got a perfect square for the x squared, and we've got a perfect square for this positive 49. We notice that we have a negative 14x here, so we're going to need a negative sign as part of our factors. So let's go ahead and set up our two factors. We know that the square root of x squared is x, so let's go ahead and pop that into there. The square root of 49 is 7. And because we have a negative sign here, that means that the sign in both of our factors has to be negative. And we can verify once again, if we take 2 times the square root of x squared, which is x, times the square root of 49, which is 7, but since it's a negative 14, we want a negative 7. If 2 times x times negative 7 gives us negative 14x, then we've done it. We have found that this is a perfect square trinomial, and we can simply factor it as x minus 7 squared. Now for the two questions that we've just done, like I said, it's actually much simpler if we factor these using decomposition or inspection. But for a question such as this one here, 16x squared plus 24x plus 9, seeing that it's a perfect square trinomial will actually be much faster in this case. So 16x squared we know is a perfect square, and 9 we know is also a perfect square. This positive 24x tells us that we need a positive sign in both of our factors if it is a perfect square trinomial. So let's go ahead, set up our two factors. The square root of 16x squared is just 4x. So let's go ahead and pop the 4x into there. The square root of 9 is 3. And because we have the positive 24x here, we know that our sign in the middle has to be positive for both of these. We can verify that this is a perfect square trinomial by going 2 times the square root of our first term, so 2 times 4x, times the square root of our last term, which is positive 3. So 2 times 4x times 3 does in fact give us positive 24x, so we know that this is going to be a perfect square trinomial, and we get 4x plus 3 squared. So this would be an ideal situation where using our knowledge of perfect square trinomials would actually help us get the solution much faster than decomposition. Taking a look at this problem here, we can go ahead and do the same thing. We know that this is a perfect square and this is a perfect square. We note that this term in the middle has a negative sign, so we're just going to keep that in mind. So once again, let's set up our two factors. The square root of 4x squared is 2x, and the square root of 25 is 5. Since we have this negative sign here in the middle, we're going to put a negative and a negative. And let's verify that this is actually a perfect square trinomial. We can go 2 times the square root of 4x squared, which is 2x, times the square root of 25. And since we know that there needs to be a negative, it's really actually negative 25. So 2 times 2x times negative 5 gives us negative 20x. So we know that it's a perfect square trinomial. And we can rewrite this as 2x minus 5 squared. Like always, make sure that you guys verify your answers whenever possible or whenever you have time to make sure that once you've multiplied these binomials out, we end up with the original trinomial. For this last question here, we're going to do exactly the same thing. This is a perfect square, and so is the 4b squared. So let's go ahead and set up our two factors. The square root of 49a squared is just 7a. The square root of 4b squared is 2b. Since we have this negative here, it ends up being a negative 2b. We can verify once again that this is actually a perfect square trinomial by going 2 times 7a times a negative 2b. When we multiply this all together, 2 times 7a times negative 2b, it does in fact give us negative 28ab. So thus we can simplify this as 7a minus 2b all squared. Now another type of special trinomial that we take a look at in this outcome is called a difference of squares. Something that we'll notice about the first and the second or last term here is that both of these are perfect squares. X squared and 25 are both perfect squares. X squared and 9 are both perfect squares. That's where this squares part comes from. Now next, when we look at the word difference, that comes from when we subtract two numbers. Now in this case, we're subtracting two squares, and that's where that minus sign comes in. So we have a difference of two perfect squares. Now before we go and factor these in a special way, let's go back to factoring this using decomposition. I can actually rewrite this as x squared minus or plus 0x minus 25. This would give me an a value of 1, a b value of 0, and a c value of negative 25. This means that something times something has to equal to a times c, which is negative 25, and something plus something has to equal to b, which in this case is equal to 0. The only numbers I can use are 1 times 25 and 5 times 5. Now since we have a negative product, that means that one of our numbers has to be negative. Now in this case, it doesn't really matter which number is negative because we know that the sum has to equal to 0. Well, the only one that would make this work is if we have negative 5 and positive 5. So breaking down this 0x as negative 5x plus 5x gets us started here. We have x squared minus 5x plus 5x minus 25. We can pair these up, pair these two up, and then factor out our GCF. So in this case, the GCF is x. We're left with an x minus 5 inside of the brackets. We factor out a 5, we're left with an x minus 5. This x minus 5 comes to the front. And in our second factor, we have x plus 5. All right, cool. So we have something that looks pretty much the same, with the only difference being the plus and the minus signs. All right, let's keep that in mind as we work through this second example. Once again, we can rewrite this as x squared plus 0x or minus 0x, it's up to you, minus 9. We get a is equal to 1, b is equal to 0, c is equal to negative 9. So we want something times something is a times c, which is negative 9, and something plus something is equal to b, which is 0. We'll see pretty quickly here that the only possibility is going to be negative 3 and positive 3, which means we can break this down as negative 3x plus 3x. The x squared stays the same at the front, and the negative 9 stays the same as our last term. We will break these down into pairs, factor out the GCF of both. So x is my GCF for the green pair, and 3 is my GCF of my blue pair. So we'll see that the x minus 3 comes to the front, and then x plus 3 is left as my second bracket, or second factor rather. Once again, we notice that the only difference between these two factors is the plus and the minus sign. Now take a look at the factors of your difference of squares here. In both situations, what do you notice? What are some relationships that you see forming between the factors here along with the original polynomial? If you said that the first term here, the x, is the same thing as your first term squared, and the negative 3, if you were to square this term, it would give you your other perfect square here. If you said that, then you're absolutely right. We've been able to pick out the characteristics that help us determine if something is a difference of squares and whether or not we can factor it fairly quickly. So all we need to do when we're confirming if something is a difference of squares is we're going to, first of all, look for a negative sign. We can see that in these first two examples, we have a negative sign, and that the first term is a perfect square, and the second term is also a perfect square. So these two examples fit the criteria for a difference of squares, and we can factor them as such. All we need to do is set up two brackets for our factors. One is going to be plus, one's going to be minus. Again, it doesn't matter if I put a minus sign here and a plus sign here. We can switch up the order and it doesn't matter. I'm going to take the square root of x squared, which is x, pop it in as my first term in each factor. I'm going to take the square root of 144, which is 12, and put that in as my second term of each factor, and we're done. We factored x squared minus 144 as x plus 12, x minus 12. I can do the same thing for the second example. I'll set up my two factors first. I can make this one positive, I can make this one, or rather I can make this one negative and make this one positive. Again, it doesn't matter. I'm going to take a look at my square root of x squared, which is x, so I'll pop that in as my first term, and the square root of 36 is 6. So I can factor x squared minus 36 as x minus 6, x plus 6. If we take a look at this third example, this x squared plus 4, we'll notice fairly quickly that this is not factorable. Okay, so let's go ahead and we'll say not possible to factor further. And the reason why is, let's say we decided to rewrite it as we did on the previous page, x squared plus 0x plus 4. This means that we have a is equal to 1, b is equal to 0, and c is equal to 4, which means that we want two numbers to multiply to give us 4, and the same two numbers to add up to give you 0. It's not possible to find two numbers to multiply to 4 and add up to give you 0, so that's why x squared plus 4 is actually not factorable any further. Something that we want to keep in mind whenever we're working with differences of squares is that we can still factor out a GCF first if we're able to. So in this example, I can factor this out, or I can factor out a GCF of 9, which leaves us with x squared minus 4. So we can factor the x squared minus 4 as your difference of squares. So we can go x plus 2, x minus 2, and your 9 can come down just in front. We can do the same thing for this example on the bottom left. I'm actually going to factor out a 16 first, and we're going to end up with 9 minus x squared. Again, all I need to do is take a look at my difference of squares here. Is 9 a perfect square? Yes, it is. Is x squared a perfect square? Yes. And we have the minus sign here, which means that this is a difference of squares. I can factor this as 3 minus x and 3 plus x. And then the 16 just comes down in front as your GCF. For this last problem, we'll notice that there's no GCF, which is fine. And we also have two variables, again, which is completely fine. We know that this 81x squared is going to be a perfect square, and this 49y squared is also a perfect square, and we have this minus sign in the middle, so we can factor this as a difference of squares. So let's set up our two factors. Let's make one positive, one negative, and we're going to take the square root of 81x squared, which is 9x. So I'm going to put 9x at the front. And then the square root of 49y squared is 7y. So we have factored this as 9x plus 7y times 9x minus 7y. Here we can take a look at a couple of examples of applications of factoring. In question number 1, it says that a rectangle has an area given by the polynomial below. What is the length and width of this rectangle? What we'll notice here is that we have a polynomial with 4 terms, and right away we should try to factor this by grouping. If we factor this by grouping, we'll end up with 2 factors, which will end up being our length and our width. So let's go ahead and try doing that. So grouping up my first 2 terms, grouping up my last 2 terms, we can factor out a GCF of 3a here, leaving us with 2a plus 3c. I can factor out a plus c, or positive c, leaving us with 2a plus 3c. This 2a plus 3c comes to the front, leaving us with 3a plus c as our second factor. So it doesn't really matter which one we call the length and width. Let's just call 2a plus 3c our length, and 3a plus c will be our width. In question number 2, it says the volume of a rectangular prism is represented by the expression 8x cubed plus 6x squared minus 2x. Determine one set of possible expressions for the dimensions of the box. So really just the length, width, and height. The quickest way to do this is we can notice that the GCF that we can factor out is going to be 2x. So I can actually rewrite this as 2x times 4x squared plus 3x minus 1. So what this gives us is we have a coefficient that can be a standalone factor. We have an x, which is also a standalone factor. And finally, we have a trinomial, 4x squared plus 3x minus 1, which can be the third factor. Now what this gives us is some combination. We could say that the width could be 2. We could say that the length could be x rather instead of 2. So length is x. And finally, our height could be 4x squared plus 3x minus 1. So this would be the quickest way to do this type of problem. Last but not least, question number 3 says a rectangle has an area of 2x squared plus 5x minus 12 square meters. Find the expressions for the length and the width. All we really need to do is to factor this using decomposition. So here we have a is equal to 2, b is equal to 5, c is equal to negative 12. So we have something times something has to equal to a times c. So in this case, 2 times negative 12 is negative 24. Something plus something has to equal to b, which is 5. So our first step after this is to find our factors of 24. So 1 times 24, 2 times 12, 3 times 8, and 4 times 6. Since we have a negative product here, we know that one column has to be negative, but we don't know which one. So we're going to go ahead and take a look at our sum. Since our sum is positive, then all of our smaller numbers need to be negative. So in doing so, we notice that the only combination of numbers that works is negative 3 and positive 8. So let's go and use those two numbers to break down that positive 5. So let's go negative 3x plus 8x here. We've got 2x squared minus 12 there. We can group the first two, group the last two, find my GCF, which is x. I'm left with 2x minus 3 inside. My GCF here is 4. I'm left with 2x minus 3 once again. The 2x minus 3 and the 2x minus 3 come to the front. And then we're left with x plus 4 as your second factor. So taking a look at our two factors here, we can consider either one the length or width. Let's just say that the 2x minus 3 is our length and the x plus 4 is our width. This brings us to the end of the AN5 outcome. I hope you guys enjoyed this video. Once again, if you have any questions or comments, please leave them down below. Thanks again for watching, and I'll see you in the next video.